Thank you for joining this webinar. This builds from our earlier beginner's guide to checking, cleaning and tidying data. As always, I'll be presenting from within Displayr as it's designed for interactive presentations, but everything I show you can be done in Q as well. So if you're a Q user and you're wanting to know how to do it, ask me and I'll show you at the end of the webinar. How do you ask me? Well, if you have any questions, jump into the little questions field in the GoToWebinar app and type them in, and I'll get to them at the end of the webinar. As discussed in the earlier webinar, our goals are to get better quality insights and to reduce how long it takes to get them, and we do it by three related tasks: checking, cleaning, and tidying. In our beginner's guide webinar, I focused on the two basic steps of checking your data file and cleaning, tidying, and checking through all of the variables in the file. Today, I'm going to jump back into those topics, but we're also going to look at how you identify low quality cases, typically respondents in a data file, and how to use automation to check, clean, and tidy. This is the more detailed list of the topics that we're going to go through. We will kick off with a quick way of checking a data file. Both Q and Displayr have a tool that automatically checks a file and just goes through and does some of the things that we talked about in the earlier webinar. So the way to kick them off, I'll click on the data file I've got. It's a very simple little data file. And then I'm going to click here to insert a report and choose check for errors in data file construction. And it alerts me that there are some errors. It tells me it doesn't contain an ID variable, and it tells me that there's various categorical variables that probably should be numeric. And if I expand out, it shows me little tables. And so I've got this variable here, which has been set up to be categorical, but there are no labels, and the numbers are in a pattern that suggests it's probably meant to be some kind of numeric data, or maybe it's missing its labels. So that's an example of using automation. In the earlier webinar, we went through all the basic ways of checking, cleaning, and tidying. Again, we can automate a lot of these things, the things done in gray. And the way we do it is I'll check the data file that we used in that earlier webinar. And again, I'm just going to automatically run a script where we'll go tables for data checking. You can write your own scripts, and I'm showing you this in Displayr. You can do the same kind of things in R and SPSS as well if you want to, but we've done that for you already here. Tables for data checking, let's expand it out. And it's checked three of the common problems you have with data. That you've got varying sample sizes within a table, that the data may contain outliers, or that you have data with values that need checking. So if we expand it out, we can see, for example, I've got a set of variables which contains three variables, all beginning with company 4, and they vary in their sample sizes, which is commonly a sign that there's a data integrity problem, as we talked about in the earlier webinar. Here's data that's been detected to see that it might have an outlier, and a histogram to make it really obvious what the outliers are. And here's data where it's showing us particular tables where it thinks the actual values are problematic. And so you can see here it's got current on contract, and the algorithm's gone through and said, oh, hold on, look at these categories for yes, no question. There's obviously a data integrity problem, and it's highlighted them as well. This is probably the most common way of tidying in market research. You've got a table with ratings like this, and you want to create what's called a top 2 box score, like this, telling us that, say, 75% of people like or love Coca-Cola. Now, the way I've done it here is kind of useful, but generally in the data tidying phase, you want to create binary variables which just contain like, love information and nothing else. So just this column of data. How do we do that? Well, we'll go and we'll find the source data. And in various programs, there's different terminology for this. In SPSS, you go recompute into new variables. In Displayr, we select the data, ready-made formulas, and we just say we want top 2 category variables. and it's going to automatically create those variables for us. And I can drag them onto the page. And I get my summary of them, which is just this column. And some of you who are new to kind of market research might be, why do you just want the column? Well, you want it because you can then easily cross-tab it with other information. See, for example, the differences by gender. So top two box is combining together a couple of categories. There are some ugly problems in market research, survey research in general, where you want to combine large numbers of categories. And a classic type of data you've got is zip code or postcode data, where you can have hundreds or thousands of these things. Now, manually merging them to drag them together isn't really a good option. So what do? Well, we'll trace back to the source of the data. And then you have standard kind of algorithms that are designed to solve this problem. So I've selected the data. I'm going to insert, again, go into this nifty little menu, ready-made new variables, and we'll choose automatically combine by geography. And at the moment, we've got algorithms for Australia, the UK, and the US, but we're very quickly adding new ones. So you should see Canadian data very soon this week. So I'm going to go to counties. And it's going through and pulling up its little database, and it's created a new variable for me here, which I will drag onto the page. And so quick as a flash, we have various zip codes. So we're easily able to tell that we're looking in New York. Here's another kind of standard data tidying problem. We've got too many categories. Now, the reason for getting all of these categories, it's often useful to have highly granular information. In this case, it's income information. But at analysis time, what do? Well, you can merge together categories manually, as we looked at before, but standard way that most people try and approach this type of data is they treat it as numeric data. Now, let's do that. We'll take the data, select the data here, and we'll just change it and tell Displayr should be numeric, and Displayr will compute an average, and the average makes no sense. It says the average income is 21. Why is that? Let's go and we'll look at the underlying data itself. We can see what's going on here, which is in the data file, and it's standard that data files are set up this way, under $1,000 represented by a 1, 25,000 to 29,999 number by 15, and so it's these numbers that are being averaged. There's a much smarter way of doing this, again, and I'll show it to you first with a shortcut. I'm going to choose numeric variables from midpoints, creates a new variable, which I'll drag onto the page. And now I've got a much more sensible looking household income of 91,000. Let's go and look at the actual values itself and see what it's done. And what Displayr has done here is it's used a technique called midpoint coding, where it's taken each of the categories and it's looked at the lowest and highest label and just put the midpoint in. And this turns out to be an excellent way of getting numeric data from categorical data, which is what we've got here. A similar kind of technique, and this is one of these things, if you know it, it's going to be obvious, but if you don't know, it's quite magical, relates to the Net Promoter Score. Now, for those of you who aren't familiar with it, the way the Net Promoter Score works is you have a table like this of likelihood to recommend, and you calculate the Net Promoter Score traditionally by summing up the number of people who gave a 9 or a 10 response, and then we subtract from that the number of people who gave a response of 0 through 6. And our Net Promoter Score is 30.7. Now, you can do this Net Promoter Score also just by turning the data into numeric and making some underlying code value changes like we did with the midpoint before. And the way we do it, again, do a little shortcut. I select the data here, oops, and then I'm going to click this little plus button, ready-made formulas, and I choose the recode Net Promoter Score. It adds a new variable for me, so it's another numeric variable. I drag it here, and its average is shown 30.7, which is what I want. How does it do that? Well, if we click on the data itself, it's just assigned a score of minus 100 to the detractor categories, 100 to the promoter categories, and 0 to the in-between categories. Now, when we looked at the beginner's guide, with numeric variables, we focused on the minimum and the maximum, but there's a couple of other ways of checking it. One which we've already seen is to automatically identify outliers. So let me explain how that worked. I've got here some data on people's weights. The average weight, and this data is in pounds, and for those of you who don't speak pounds, 220 pounds is around 100 kilos. So the average weight in this sample is 266 pounds. And the way that outlier detection algorithms for numeric data most commonly work, and there are variations to this, is you calculate the average or the mean, calculate the standard deviation, and then somebody said to be an outlier if it's 3 or more standard deviations from the mean. So with this table here, you'd say that the outliers are people whose weight is more than 1,052 pounds, which is pretty big, or less than minus 520 pounds, which is impossible. So this is, as I said, the standard algorithm. I don't like these algorithms. And the reason I don't like them is in this example, you can very easily see that this 999 is clearly a problematic weight, but it's not apparently an outlier. Now, some people tweak this and they might use a value of 2 or 2.5. And in this case here, it means that we start to conclude that this 999 pounds is an outlier, but it's just so arbitrary, right? And we'll talk about why it's problematic theoretically in a second. But I tend to, as I said, I don't find this useful. If you want to, you can automate it, as a Displayr does allow you to do, but I tend to get much more value, and I always do this, by creating histograms or density plots and examining their shapes. Now, there are two standard shapes in data analysis, which are good shapes. You can have your classic bump or hump or normal distribution, and if you've got that in the data, you tend not to have a problem. But we tend not to see it in survey data. We're much more likely to see this thing called the skew right distribution, which tail goes off forever. It's much more common in data that we've got, such as income data, wealth data, how much people purchased, things like that. And that's fine. It tends not to be a data integrity problem, but we often need to use a technique like banding to tidy it. We'll return to that. And these are the problematic types of shapes. If you've got multiple bumps, it could be an insight, almost always a problem though, or small number of outliers, you can barely see them here. That tends to be a problem as well. But let's go back to our case study. Here we've got our weight data. We're going to convert it to a histogram and have a look. So what can you see? That's right. We've got the bump, and then we've got a whole lot of little outliers up here at 999. So there's clearly something weird going on. This is not an insight. Let's follow back and look at the underlying raw variable itself. Click on this values button to see what the actual unique values people have entered. We'll scroll to the bottom. And so here we've got some sensible sounding weights, 298 pounds, but all of a sudden it just goes crazy with people in the 990 categories. What's that about? Is there like a small family of elephants that have learned to use computers? No. In non-online data, such as phone data or face-to-face interviewing data, there's a common convention that you indicate missing values by writing 99 at the beginning. And so there's often codes like 996 might be interviewer too embarrassed to ask, 997 might be respondent said don't know, 998 might be respondent refused to answer. And so the standard way that we deal with this is if we've got a way of getting the truth, we put it in, which is called imputing. But if we really have no knowledge at all, we're going to exclude it from the analysis, which is what I'm going to do now. And now it seems to be a lot better, but look at this as this weird kind of saw pattern here. What's that about? Well, what we're going to do is we're going to modify our histogram now to increase the number of categories in it, number of columns. If we had density plot, we'd reduce the bandwidth. Right, it's a little hard to see now, but we've got this really interesting pattern. Bump at 100, bump 105, bump at 110, bump at 115, 20, 30, 130 here, 135, 140, 130, 45, 150. We have a pattern that occurs very commonly in survey data called shelving. People don't tell us their height is, this is in centimeters, so weight is, 163 pounds, they round it, 160, 165. And so that's what we're seeing here. And so we can infer from this that we don't have accurate weight measurements. We've got people's recollections, which is good to know as well. So once you've cleaned your numeric data, how do you present it? Because we can compute the average, but the average really isn't on its own enough. And it's really hard for most people, including me, to understand what standard deviations mean. And so the technique that is most commonly done is to do something called banding. The way banding works is, and we'll choose this weight data. I'm going to insert a new data here, and we go into this great new thing, which I showed you before with geography. Now I'm going to do by value, and this is something our data science team just released in the last couple of weeks. And I'm going to create percentiles first. And it's going to create deciles, which means 10 categories of percentiles. And so it's added a new variable here. I'll drag it onto the page. And so this is the percentiles. Now, some of you might be going, they're not exactly 10%. And it's because with most types of survey data, it tends to be discrete. That is, there's not an infinite number of possible values. There's a whole lot of people who may have given the same answer. So you can't make your percentiles completely equal. Now, a more common kind of thing that a lot of people like to do is quartiles rather than looking at deciles, 10 categories. And so to put quartiles in, I'll just say I want to do 25%. And again, they're not exactly 25%. And for this reason, percentiles, quartiles and stuff are actually not that popular in survey research. And what most people instead to do is they might go with equally spaced categories. Let's have 4 of them. And so if you want to have categories where you have equal values between the bands, it would look like this, but you probably want to tighten that up. And I'll go with tidy categories. And so now we've got pretty neatly defined categories which summarize that numeric data, which we can then cross-tabulate with other data. So that's called banding. In the beginner's guide, we talked about how sometimes text variables shouldn't be text variables. Another problem that we commonly need to check for, particularly with low quality data sources, is if we've got duplicate responses. And this tends to show up where you've got an open-ended question and someone's given a kind of a really long rant, and then you check and you discover that another person's given that same rant, which is just impossible. We talked about how to detect duplicates in the earlier one. Another kind of classic issue is poor quality text. So here we asked people what they disliked about their phone company. And somebody said, "It is well with my soul." Now, maybe they're a poet, or maybe they're just not doing our survey very seriously. Now, some people misunderstand this and they go, "Oh, it's all right if people give a couple of bad text responses, I'll just treat them as missing data." I don't think this is good practice, because most survey questions don't give us any way to check if the respondent has made a mistake or given us bad data, right? All we can see is their answer. If they tick they were male, we just don't know. It's only in the open-ended responses that we get a good read on whether they're giving us garbage. And if they're garbage, probably the respondent is garbage, and we should delete that actual case, as we talked about last week. I'm always surprised about how many people don't know what backcoding is. It's a lovely little tidying technique. Here we have data showing us what household structural living arrangements people have. And one person chose the other box. And if we look at their other box, they said they're a single mum. Now, they're not other, right? That should just be living with children only. And so backcoding is the process of pushing that data and tidying it all up. How do we do it? Again, we'll select the table and we'll follow the link back to the source data, because you can see I've got lots and lots of data files in this example. And click on the text data, and now we go down to text categorization. And I click on this special button called Inputs and Backcoding, and I tell it I want to overlay this with my living arrangements data. And so now it's added these categories. I'm just going to remove this new category, which I don't need. And I'd use that if I had some new phrase because I've forgotten some type of category. But this single mum, I'm just pushing her into living with children only. Now a new variable has been added to my file. So I will replace my little variable up here. Resize my table, and the other is now sitting at 0, which is what I want, so I can delete that from my table. And now I've tidied up my data. Now, backcoding is a useful technique, but the main real type of coding is for categorizing data, text data. Now, so coding is the market research jargon for text categorization. Yes, it's very confusing because it doesn't mean computer coding at all. It's not programming. How do we do it? Well, I've got this data which we started looking at before on why people just like the phone company. And so again, I'm going to go down here. I go text categorization. I've got a couple of options here which we talk about in our webinar on text categorization. So I'm not going to go through them here. I'll just show you the basics. All right, so I've got 272 people who said there was nothing that they disliked, so I'll create a new category for them. The next person's mentioned service, and there's lots of different meanings of service. I'm just going to write customer service. I'll just do a quick search for customer service. Chuck them across. All right, so we've started our coding. I should have got the nothing people across. Let's put the nothing people there as well. Now, we've got lots of great machine learning techniques, so check out the webinar on that. For the moment, I'm just trying to show you what coding is. So click Save Categories, and new variable appears in my data file, and then I can just analyze that like any other variable in my survey. Okay, so we're now going to do a deep dive into missing values. Here I've got a driver analysis, and don't worry too much if you're not interested in driver analysis, because the principle I'm going to go through here is very generally applicable. If you look at the footer, it tells me that I've got 482 cases in my total data file, but only 372 in my analysis. And that's telling us that the difference between that 190 are missing values who have been excluded from my analysis. Is this a problem? Well, the way you work out it's a problem is you compare if those 190 people are fundamentally different to the other 372, because if they are, it follows that this analysis will be wrong. There's lots of ways you can do that, but if you like to formalize the approach, the great statistician Roderick Little, who's actually invented a lot of the techniques used for missing data, we'll type his name in here, and it'll show us what technique he's actually got his name on, which is a nice thing called Little's MCAR test. Missing completely at random, it stands for if you need to know. And so what we're going to do now is we're going to find the variables that are used in our actual satisfaction model or net promoter score, likelihood to recommend driver analysis. I'm just going to drag them in here. And this test is just going to work out if the people who've got missing values are different, and a small p-value is a problem. What we can see here is our p-value is pretty small, and that's telling us that our earlier driver analysis is invalid because the people with missing data are not the same as the people who have data. So we need to explore a little more deeply. A great way of doing that is this particular visualization. It sits in this same missing data section here, a plot by case. Now what a plot by case is, we drag across the same variables again, and it's going to show us one row represents each person in a heat map, one column each variable, so it's going to be a very busy heat map. And we're looking for patterns in the data. Now, there's a vague pattern here, which is some variables have more missing values than others, and we should definitely look into that. I'm not going to now because we're just going to jump into the specifics of this data file, not be so interesting. But what would be a problematic pattern? Well, when you've got something bad, it tends to appear as big blocks and things, quite irregular shaped patterns here, and we don't have that, which is good news. Another type of way of exploring missing data is to look at a plot of patterns. So again, it sits in that missing data folder. I drag it across. And the way this one works, and it's really small fonts here, again, each column is a particular variable, and the bottom row is the most common pattern, and it's got the biggest bar. And if you really squint, it says there's 372 respondents, which is the people with complete data, and the blanks mean they've got no missing data. The next most common pattern is that this second last variable here has got 33 people who've got missing values, and another one. And so again, we should look at these patterns, but again, there's nothing obviously weird here. It's the kind of normal type of pattern that you'd expect to see, so that's good. Why is that good? Well, it's good because our situation is this. We know we've got missing values. We know we can't ignore them. We haven't seen any ugliness in the patterns. And so what should we do? Well, one thing we can do is we can attempt to guess what the missing values should have been. This is a technique which statisticians call imputation. So imputation is just statistical speak for guess, but you can have good guesses and bad guesses, right? So how are we going to do it? I've got here a very small data file. We're using a really small data file because it will just make it very easy for us to see what's going on. So I'm going to select 3 variables in the data file, and we'll just view them in the data editor. Drag that up. All right, now you can see here that for the age data, we've got missing values for 6 people. What should those missing values be? I'll give you a chance just to try and work it out, because this is a problem that you can actually solve. Okay, so I didn't give you a lot of time, but notice something here. Everybody with missing data is not married and doesn't have children. And if we look through this data and find other people who are the same, so let's row 10, row 8, row 20, we see there's kind of, as you'd expect, they're more likely to be younger. All right, so we're now going to get Displayr to impute or guess the values. And we're just going to click on the age. And again, we're going to go into this lovely little ready-made new variables, and we're going to choose impute missing data. And this is also in Q for Q users. And so it's added this variable, and let's just drag it onto the screen so we can look at it. And it's gone, and it's concluded that 2 of the people are 18 to 44, and 4 are 45 or more. And you might think, well, that's not what we thought before, right? And it's because all we've done is told it to look at age on its own. And so it's just noticed that in the data in general, 45 or more is common. So it's going to guess that these people are more likely to be 40, more of these are 45 or more than are 18 to 44. So what we need to do is we need to actually improve our model here by adding in auxiliary variables. So when we click on the actual age variable here, it shows us that it's imputed age, and auxiliary variables are additional information that we're going to use to predict. So it's like having predictors in a regression model or a driver analysis. And as we add that extra information, you'll see it's updated here, and now it's showing that the vast majority of them are 18 to 44, which we'd expect, but 1 is 45 or more. Now, you would be right to go, wait a second, why is respondent number 1 45 or more and the rest 18 to 44? That doesn't make sense. And in the world of predictive modeling, it wouldn't make sense. In the world of imputation, it does, because when you impute data, you want to come up with sensible guesses, but you also want to make sure that your data file contains the same level of variation as a real data file. And in the real world, there are people 18 to 44, sorry, age 45 or more who are unmarried and don't have children, and so you want that to be reflected in the imputation. But the algorithm, which is doing the imputation, it doesn't know which person should be 45 or more and which should be 18 to 44. We haven't given enough auxiliary variables to work that out, so it's just guessed. And this guessing is done via a seed. A seed here just means guess number, and you can change this and it'll just give a different guess. Well, now everyone's 18 to 44. Now this person's 45 or more. And so this is a potential problem with imputation. Each time we do it, we should get a kind of different answer, and that makes some people uncomfortable for a good reason, because it just means your data is not stable. So how do we solve that problem? Well, we will return to our driver analysis. Here's the driver analysis we had before. We're gonna, rather than manually impute the data, we're gonna use this awesome little inbuilt feature here, and we're gonna choose missing data, multiple imputation. And what multiple imputation does is it imputes the data once, builds a regression model. Then it imputes the data a second time, so with different randomness, builds another regression model, and it repeats this multiple times, and the output is just the average answer across all of those multiple imputations. And by using the average, it avoids the results being sensitive to the imputation, and it actually makes it easy to compute accurate p-values. So it's a doubly cool technique. I would stress this is in no sense a Displayr invented technique. This has been best practice when dealing with missing data for many years, and best practice for certain types of missing data. I'd encourage you to check out the webinar on driver analysis, because in that we actually even talk about how for this data there's an even better technique, which is something called dummy variable adjustment. We explain why, but that's not really a data cleaning issue. So far, we've seen that a lot of data cleaning and tidying involves creating new variables. I'm just going to show you some other ways of creating new variables, and these are particularly power techniques. So this might do a few of your heads in. Don't worry, not for everybody, but we promised this was an advanced webinar, and so it is an advanced webinar. So what we're going to look at now is doing mathematics on sets of variables. Now, in my file here, which is the phone data that we used in the earlier webinar, I've got 18 separate things where people have said how many hours they spend per week doing each of these activities. And you can see here, personal calls on average was 0.3 hours, watching TV 2.2 hours. But then they asked people how many minutes they spent. So remember, 0.3 was the first one. And we can see that on average in minutes, people spend an average of 12 minutes in this first category. So we need to combine these bits of data together. How are we going to do that? Because the correct answer for the weekdays for this first category should be the 0.3 hours plus 12 minutes. 12 minutes is roughly 0.2 of an hour, so we should be seeing 0.5 is our correct answer. How do we get there? First thing we're going to do is we're just going to click all of these minutes variables here, and you can see there's 22 of them. And then we're going to go into calculation, and we're just going to go divide. And so this is going to do the calculation. I'm going to divide by 60, so I'm turning my minutes into hours. And then I drag this new data across. And now it's showing the 0.2. So we've converted my minutes to hours, and we just did it with a couple of mouse clicks. And because we had grouped together all our minutes variables, we could do them at once. Now, this is the bit that's going to get really technical. It's just for the people who really want the technical way. There are other ways to do it. But I'm going to now click on the individual variable here, and it will show me the code that it used. And so this is how it did the dividing. And I can edit this. And I'm just going to say, now I want to add together. I'm going to add to it all of my data on minute hours. So remember, we're expecting to get the answer of 0.5 at the end. And so I'm now just writing code which applies to all of my variables at the same time. And now I've got the correct answer of 0.5. So now I've combined my minutes and hours data together. I'm going to type time spent. And then I'm going to go back to this other data down here. And I'm going to write hours do not use, just to remind me that this data, I don't want to inadvertently analyze it because it's my input data. As promised, a really advanced topic. So there is some really complicated stuff you can do if you want to do, but you can just do stuff a lot easier ways too. And now we move on to the next topic, which is identifying low quality cases, which typically you would delete from your data set. And we have already looked at a number of ways of doing that. We've deleted people who've got poor quality open-enders. In the previous webinar, we deleted people who were missing values on key variables or have too many missing values. Another way of doing it is to delete people who failed the lie test. Now, psychologists have got a very standard way of doing this, which is they say to you, do you ever tell lies? And anybody who goes, no, I never tell lies, the one thing the psychologist knows is they're a liar. And so you can do that in a survey, and I have done that in a survey. The more orthodox way of doing it in market research, of course, is to show people lists of brands and ask them if they've purchased them. Another standard approach to checking respondent quality is to look at the time taken to complete a survey. We look for speeders, that is, people who have completed the survey in an implausibly short time. Now, the way I've done it here, and I've got some data on seconds, and I've just done a histogram, and this is one of those standard shapes, which means we tend not to have a problem. If we had a spike down here, that would tend to indicate we have a bit of a problem. You can also use your judgment. So in this case here, our lowest value is around about 300 seconds, and you can use your judgment, is it possible for somebody to have done my survey in that amount of time? Returning to our earlier regression or driver analysis, with most advanced predictive models, they're automated approaches to identifying outliers, and they're model-based. Now, we've actually already done a model-based outlier detection. That initial thing where we looked at the standard deviations of 3 or more from the average to find outliers, which I wasn't comfortable with, you'll recall, that is model. There's model. And what is the model? The model underlying that approach is the assumption that our data is normally distributed. And if our data is normally distributed, then an outlier that's more than 3 standard deviations from the mean is certainly a problem. However, market research data is very rarely normally distributed, which is why that was a bad model and it didn't work. Here we have our regression model. And if we look over it, it's actually alerting us, a little warning here, that we've got unusual observations and tells us what to do. But we're gonna, and if you check out the webinar driver analysis, you can get more information on what to do, but we're just gonna focus on these unusual observations. We want to learn who they are so we can do some more investigation. How do we do that? Well, we scroll to the bottom of the form down here, and it's got all these diagnostics we can click. So I'm gonna choose Cook's distance. And these are all just different definitions of outliers. And the idea is you look at the outliers and then you investigate their data, just like with any other data, come to a conclusion. Should there be missing values? Do I care? Here it's telling us we need to particularly focus on respondents 74, 264, and 418. So we'd want to go and look at the raw data of those and just try and work out if we think they're plausible or not. In max-diff and conjoint data, we tend not to have useful ways of defining outliers, and that's because the data is categorical and tends to be, the data itself, for various technical reasons, doesn't fit well with traditional outlier models. So what we instead do is we see how well the models predict. That is, for each person, we go, okay, you've given answered 6 questions, for example, in our survey, how well does the model predict your accuracy? Now, you don't just count up the number of choices. There's a special measure that you want to use, and this is something called the RLH, or root likelihood. And again, it just appears as a diagnostic. You click on your model, you scroll to the bottom, root likelihood, and it's going to add a variable to my data file now for my max-diff. Same for conjoint. It contains that root likelihood. I'm going to drag it onto the page. And as with before, we're going to explore it using a histogram. So distributions, I'm always choosing this categorizable histogram. It's my favorite histogram. Now, there are some basic rules of thumb. So in the case of the RLH, in this max-diff study, I showed each person 5 alternatives. And that means that my RLH really needs to be bigger than 1 in 5. Number of 0.2, which would suggest my RLH cutoff should be about here. But I look at the histogram and I see that there's this nice big bump of people, and then there's this cutoff and people below that cutoff. And so there seems to be this segment of people for whom the model predicts badly. And so in this case here, when I did do my proper analysis, I just used people who had their RLH greater than 0.4. So again, using the histogram as my way of doing my cutoff. It's important to stress that with model-based outliers and this low-quality respondents, it could be that the respondent's garbage data, or respondent has garbage data, or it could be the model itself has a problem and doesn't fit the data very well. And if I click on this model, I actually get these little weird technical warnings, and it's telling me that I've actually probably got to improve my model. And that is common, right? And that's the challenge with model-based outlier tests. The model can be wrong. Another standard way of looking for low quality respondents is to look for flatlining or straight lining. And this is when people have given the same answer to lots of questions. And so in this data here, I've got respondent 37. It gave the highest score for likelihood to recommend. It's chosen 5 out of 5 for all my satisfaction scales, 5 out of 5 for everything I asked about customer effort. So it could just be they love us, or it could be they just clicking that rightmost option of straight lining, flat lining, depending on the term you like. Now, rather than read through the file, the way I can do this is I can just, again, click on the file I'm interested in, go down, scroll down, find a new report that I want to add, and the straight lining or flat lining report. and it's going to add some tables, and it's showing me, and these are the names. So one of my questions in my survey sets of variables is called company for, another is called time, and it's just showing me that 3% of people go flatlining here, and so on and so forth. And if I want to, I can actually follow back through the data and identify who those people are. Another pretty orthodox approach to tidying data sets when you've got large numbers of variables is to use principal component analysis or factor analysis. And we've got a whole webinar on this, so I'm going to go through this very quickly, but the basic idea is you run the analysis, you drag across your variables, and in my case here, I'm going to again use this data that I've been looking at on my driver analysis, so my likelihood to recommend. And what this analysis is showing us is that we can, of these 10 variables I've used, we can explain about 67% of the information if we just replace them with 2 variables, elegantly called component 1 and component 2. I wouldn't bother in this study, but where you've got surveys where people have asked many dozens or sometimes hundreds of rating scales, it makes a lot of sense to use this approach to grading new variables. And we're very close to the end now. With tracking research, a common problem you've got is you do your data cleaning, and then every wave of survey, you've got to do your data cleaning again, and that gets real tiring. So you want a way to automate it. I'm going to show a quite exotic example of how to do this. Here I've got a table which is showing me on the columns my weeks of surveying, in my rows gender. And I've put onto this table the corrected p-value, and that's just a little statistic I can choose from my menus here, both Q and Displayr. And these corrected p-values, they'll get less than 0.05 if there's a significant difference between my genders from week to week. Now, at the moment, they're all showing 0.23, and most people use a cut of 0.05. So I would say that the gender variation is okay. And it says down here, the gender variation in gender is not statistically significant. And if I click on this, I can see I've got this code, and this code, it's a simple bit of code, but you just cut and paste, it's easy to modify, is just looking at this table, and it's gonna, whenever it observes that these values get less than 0.05, it'll show us an error. How do we do it? I'm just gonna swap my data file here. And I'm gonna choose a new data file, which has got 12 weeks of data in it. And as you'd expect, the table at the top has been updated to add all the additional weeks of data. The color coding is telling me I've got significant variation, but more importantly, can you see here on the actual page on the left, it's got this big error on it, which I can't miss. And if I click here, this is actually the error, and it's telling me that gender is varying significantly over time, which is, it's just summarizing the results in the table. But this is a very helpful approach, right? Because you write your data cleaning tests just once on your first wave, and then every time you update, just click on the page and it'll show you if you've got a problem. So this is the summary we used last week, and it's again the summary of this week of all of the different techniques for checking, cleaning, and tidying data files. We've been through them all now, pretty much all. We didn't do merging files. In 3 weeks' time, I've got another webinar on a beginner's guide to tracking or longitudinal research. So if you've not done that before, you're just starting doing it, check that one out. Yes, we will send you later this week, or maybe early next week in reality, a recording of this webinar as well as a link to the slides in this webinar. And so if you've got any questions, please add them into the questions field in GoToWebinar, and I will answer them now. So the first question we've got from Larry, g'day Larry, is automatically combined categories available in Q as well as in Displayr? Let's go have a look. So this is Q, if you're not familiar with it, I'm going to type automatically combine. I'm going to automatically combine variables, and it's showing me here that it is not all in Q quite yet, but it's going to come into Q very early next week. I actually thought it was in Q today. Oh, wait. No, it's not there, is it? It's not there. I'll just quickly go here. Let's go into create new variables. Too many options is the problem. And I'm wrong, it is here. Way. Okay, so we've got the by value. They don't have the geography data in yet. Now, the problem with the geography data is there's really huge data files. So I have to go and talk to the the data science team, and find out if the number of geographic data is so big that it can't be provided in Qt, because it would have to do it over the web. Anyway, but we will talk about that when we send the email out to everybody. Oh, Larry already found it. I should have gone to the next category. All right, and Kevin asks if the imputation is available in Q. And again, type impute, and you can see it is there. We do have create new values for impute, so that is cool. The next question we've got is, do we have to use histograms? Thank you, Barry. You don't have to use histograms. So I said here histograms or density plots. If you go into the visualization menu, we've got lots of other kinds of things you can do. You can do violin plots, box plots, whatever you like. I tend to prefer to use histograms because I like to play with that bin width to look for that kind of shelving effect. Cool, and that is all the questions we've got. So thank you very much for joining this webinar. If you're one of our customers, thank you very much for being one of our customers. If you're not a customer, hopefully you've seen something that makes you think, I need this software, and you'll get in contact and we'll do a demo. Anyway, enjoy the rest of your day, everybody. Bye now.